So this is a weak acid conjugate base buffer. Whoops. This is the formula we would use. What's the formula for a weak base and conjugate acid buffer? Well, that would be the POH equals the PKB plus the log of the conjugate acid over the base. So tuck this formula away somewhere. Now I want to mess with our buffers. I want to mess with our buffers. And this requires what are called BAA tables, which I like to call BAA tables, right? And before we get into any of that, though, you have to get good at identifying when I add an acid or a base to a buffer, which component of the buffer is it going to react with, and can you write an equation for it? So if you give me a second, I'm going to draw our buffer up here. So here's our buffer. We have a weak acid conjugate base buffer. It's got acetic acid and it's got acetate. And here's what I want to do. I want to add two things. So I want to add a base, sodium hydroxide, to this buffer. So my question to you is, if I add sodium hydroxide, what is it going to react with? Well, sodium hydroxide is a strong base, and the base is going to react with the acidic component of the buffer. And I want to write an equation for that. So what's that going to look like? Well, it's going to look like you got a couple options. NaOH plus H C2H3O2. That's going to make NaC2H3O2 plus H2O. Or you could get rid of the sodium. The sodium is really just a spectator ion. So the other option is you just show hydroxide, because the sodium doesn't do anything. So we could show hydroxide reacting with the acidic component of the buffer, and then that would just be H2O and acetate. So it doesn't matter whether, either way, whether you have the sodium there or not, that's what's going to happen. So the first thing, when I add something to my buffer, I have to say which part of the buffer is it going to react with. If I add sodium hydroxide, it reacts with the acidic part. And then can you show me an equation showing that reaction of the base reacting with the acidic part of the buffer? So now, what happens if I add a strong acid like HCl? What's that going to do? Well, a strong acid is going to react with the basic part of the buffer. And now we need to show that, okay? The base is going to grab that hydrogen, and we will get HC2H3O2 and chloride. Now, you don't even have to show that chloride, right? Chloride is a spectator ion, so it's up to you whether or not you want to show that. That would be fine, too. So here's what happens when we add sodium hydroxide. Here's what happens when we add a strong acid HCl. And you can see that this buffer is doing buffering things, right? It was able to withstand a base being added to it because I had an acid in there to suck it up. And it was able to withstand an acid being added to it because I had a base in there to suck it up. So it can do both those things. So the first thing, when you get one of these addition of an acid or a base problems, the first thing you have to do, and that's what we just did down here at the bottom, is you have to say, okay, if I add base, who does it react with? If I add acid, who does it react with? And then can you write an equation? So let's start by this. Let's define our buffer. So we have, let's do 1.00 liters of a 0.100 molar acetic acid and 0.100 molar sodium acetate. buffer. And I'm going to draw a picture of this guy over here. So there's our buffer. All right, there's still some Windex on the board there. And man, we're going to add some stuff. We are going to add, oh my goodness, I don't know. Let's add 0.0500 moles of sodium hydroxide to this buffer. And I would like to know what is the pH after the addition. Okay. And furthermore, let's assume for these problems, because this is what's going to make this easier, let's assume the volume doesn't change. Here's how I do this. First thing we need to do is write the reaction that's going to take place. So if we add sodium hydroxide, it's going to react with the acidic part of the buffer. Now you need to make the decision, are you going to include the sodium or not? We can include it, I don't care. Let's write this out. So we're going to have sodium hydroxide reacts with the acidic part of the buffer. Since that's strong, single-headed arrow. You don't need a double-headed arrow here. And we're going to get water, and we're going to get sodium acetate. Awesome. Now, the key to these addition to a buffer problems is to, after you write your reaction, make a BAA table. The B stands for before the addition. The A stands for the addition. What are you adding? And the second A stands for after the addition. And the key to a BAA table, and this is one of the most important things I'm going to say tonight, is that everything must be in moles. Everything must be in moles. So it looks like a nice table, right? Take a second. I'll let you catch up with your beautiful table there. So everything in this table has got to be in moles. So this first column is for before we add the sodium hydroxide. So before we add the sodium hydroxide, there's no sodium hydroxide in there. So that gets a 0. By the way, water, pure liquid, that is not involved in the reaction. It's just the solvent, so you can kind of shade that column out. So now I need to know the moles of acid, of acetic acid, and the moles of sodium acetate that were in this buffer. How do I get that? I take the concentration, I'll go up here, take the concentration and multiply by the volume. We have 1 liter. And you can see that comes out to 0.100 moles. We're going to do the same thing for the sodium acetate. So 0.100 moles of sodium acetate. And again, we have 1 liter. So it comes out, again, we got to start somewhere. We're going to do a really easy problem. That's 0.100 moles of sodium acetate. Now, what are we adding? We're adding 0.0500 moles of sodium hydroxide. So we're adding 0.0500 moles. We didn't add anything here. We didn't add anything here. What happens after the addition? Well, I have plenty of acid to take care of this. So what's going to happen? That acid is going to absorb this. So I'm not going to have any base left. I'm going to subtract this from there. So we're going to take 0.1 minus 0.05, and that's going to be 0.0500 moles of acid after the addition. And now we got to be careful here. What happens? Well, this is going to quench all of that, but it's going to make this much more sodium acetate, right? Think about what happens when these two react, and I'll write it down here for just a second. When these two react, you get sodium acetate and water, right? So if I react 0.0, I'm going to make 0.05 more moles of this stuff, right? If I react this much, it's going to, so this is now going to be 0.1 plus 0.0, it's going to be 0.150 moles. So let's take a second, we're not done, but let's talk about what happened here. This guy I had enough acid to cover it. I took 0.05 of my moles of my acid, and that got added over here because I made more of the basic part of my buffer. It's back up to 0.150 moles. Now, I still have a buffer. I have acid, I have a weak acid, I have its conjugate base, but it's no longer a one-to-one buffer. So what can I do? Well, I can, since I still have a buffer, I can use the Henderson-Hasselbalch equation still. Okay, but I need to turn these back into concentrations. Remember, in the Henderson-Hasselbalch equation, pH equals pKa plus the log of the basic concentration, that's the sodium acetate or just the acetate, divided by the acidic concentration, that's the HC2H3O2. So these have to be molar, they're concentrations. Now here's the good news. We said it was a 1 liter solution, and we assumed that adding the base didn't change the volume. So you just divide these by 1 liter again. And again, these problems are going to get more difficult. And this becomes 0.0500 molar, and this becomes 0.150 molar. So now we can Henderson-Hasselbalch this, right? We need the pKa. So the pKa of acetic acid is 4.74. So the pH equals 4.74 plus the log of the base concentration after the addition of the sodium hydroxide. That's up to 0.150 molar, divided by the acid concentration, that's down to 0.0500 molar. 4.74 plus the log of 0.15 divided by 0.05. And we see that the pH of the buffer is now up to 5.22. 5.22.